there's actually an analytic form of this hyperbolic, hypercube integral, basically, getting this explicitly with an analytic expression. That's not something that I'm going to dwell on in this class, although it is potentially useful. But I'm going to show you some other approaches. One of them based, it's sort of a graphical methodology for assessing this that hopefully will give you kind of a very simple, clear idea of what's really going on when we're trying to assess basically our null hypothesis under multiple independent tests. Okay, so as we first said, simply multiplying p-values, regardless of whether the original observations were actually independent of each other, multiplying p-values is not a valid way to get a p-value for that total set of observations. The best way to do it is actually to combine all of the observations into a single metric and then derive a p-value for that single metric. To a certain extent, that's kind of what we are doing typically when we're computing a p-value. So for example, you could have said back in the paternity testing example, we had these like independent observations for each SNP, right? And now we put together a composite metric that's combining all of the data for all the individual SNPs, and then we calculate a p-value on that, right? So that general idea definitely holds if you can figure out a way to take your total set of observations, the 10 independent observations, and compute an extreme value test on that total set of data. That's kind of the true, correct way to do it. Another method that I'm going to show you that's a very simple graphical method is basically to look at what we would expect the behavior of our p-value to be under our null hypothesis. And this goes straight back to what we were saying here about the uniform density of the p-value under the null hypothesis. Namely that it should just be uniformly distributed across 0 to 1. And another way of saying that is that, the p-value of the p-value is itself. So what we can do is we can simply plot our p-values sorted in ascending order versus the empirical CDF for our data. What do I mean by empirical CDF? It's like, well, empirically, in our actual data, what's the probability of getting a value this small or smaller? Well, it's just the count of the number of data points that were this small or smaller. That's the empirical CDF, okay? So when we say that, typically we call that the rank of the sorted data. In other words, you've got empirical data values, you sort them in ascending order, and the number of data points that are this small or smaller is just, I'm at position 27 in my 1,000 data points, so that's 27 over 1,000 is the probability of getting this small a value or smaller, right? By definition. So we can plot those two things against each other. According to this uniform density principle, what should we see? We should see a straight line diagonal. Should both march from 0 to 1 hand in hand in lockstep, straight along the diagonal from 0, 0 to 1, 1. You can plot that either on the linear axis, 0 to 1 increasing linearly, or on the log-log axis if you're especially interested in the region that's small numbers, right? You want to see how is it behaving down at the small values of the p-value. So that's the basic procedure outlined here. We have an observable x. We've got n of them. We sort them in ascending order. We have our p-value computed under this p-value, what's the probability of getting x less than or equal to an observed value x under our hypothesis. The empirical CDF for that is just what I said, the rank divided by the total number of empirical data points in our data set. So we plot that versus that, okay? What do we expect if our data were really emitted by our model representing our null hypothesis? We would expect to see a straight line correlation diagonal from 0, 0 to 1, 1 of that versus that, okay? Under the assumption that H truly emitted our data. If H didn't emit our data, then we're going to see deviations from that straight line diagonal, okay? So here's an example of what that looks like. What we've got down here on our x-axis is the p-value, and on our y-axis we've got our empirical rank or empirical CDF, okay? So as I said, it's expected to pass on the diagonal from 0, 0 to 1, 1, and you can see for this particular data set, it's not bad. It's pretty close. It's within the level of noise. If you saw that, you definitely would not reject H0, right? So, of course, oftentimes our interest is in the tail of low p-values, right? That's the place where we're typically most interested. If we've got a big data set, you know, those low p-values are all going to be clustered down in this tiny little spot down here. So oftentimes what we want to do is we want to expand that out by taking log-log plot, okay? So here's an example of looking at a log-log plot for our p-value versus our empirical CDF with the one slight modification that basically what we're doing is we're taking negative log, which basically flips it around so that this is the end at 0, 0 that represented 1, 1 in the straight probability versus probability. And our low p-values are now out at this end of the picture. So it's up here, we're interested, for example, you can see right up there, we're starting to get a substantial deviation from the diagonal that we expect. And in fact, the whole data set is deviating significantly from the diagonal. There's definitely something going on here that's not fitting our null hypothesis H0. Okay? Any questions about this sort of graphical approach to assessing multiple p-values?
How did you get the empirical value?
Right. So it really is just as simple as I said. So under the assumption that our p-value is looking for values less than or equal to some observed value x, then we're sorting our data in ascending order so that our small p-values are going to be for small values of x. Okay? Does that make sense?
Oh, the observed values xi is p-value.
No.
It's not.
No. The observed values xi are our actual experimental observations.
It's measurement.
Just some measurement, yeah. And then let's say that our p-value of interest is looking for small deviations. In other words, x less than or equal to the observed value little xi. Let's just say that that's the form of p-value that we were interested in. For
So xi is fixed for the whole
we've got a bunch of xi. We could compute p-values for each one of them, right? So we've got, for n observations little xi, we've got n p-values computed from them. For each one, you calculate its p-value. So let's take the simple case, what if our hypothesis really is rejected, okay? So we've got a whole bunch of experimental observations, and they all have like really small p-values, right? So I think you'll agree that what we're going to get when we display this graph is we're going to have a whole bunch of them as like really, really small p-values, whereas empirically what we would expect is just a uniform distribution across from 0 to 1. So they're going to be clustered way down at small p-values. So when we plot the empirical rank versus the calculated p-value, it's not going to lie on that diagonal line, right? You see the kind of deviation that I'm talking about? You want me to draw it?
Yeah.
So okay, so let's say that down here is going to be the p-value, and up here is going to be, so I'm going to call this alpha sub I, okay?
So it's one of the.
One of those p-values.
Okay.
Right. I've got a bunch of xi, and for each xi I calculate an alpha I. That's the p-value of xi. Okay. And on here I just plot I over n. And what's significant about I over n is recall that our xi are sorted in ascending order. So empirically, if I take the value xi and I say empirically what's the probability of getting a value of x less than or equal to xi, it's just I over n. I've got I values that are less than or equal to xi out of my total n. Okay? So our empirical CDF is just I over n. So now I'm going to plot them against each other. If the data actually were emitted from H0, then what we expect is that they're just going to fall on that diagonal or close to the diagonal within the level of noise in our data, right?
Yeah, here the I has nothing to do with the alpha I, right?
Alpha
I means you have
alpha I equals the p-value for x sub I. In other words, capital X less than or equal to the observed value x sub I given H0. Let's say that that's the definition of our p-values alpha sub I. Is this making sense? Is there a piece of this that doesn't make sense to you?
yeah,
Which piece?
that piece.
So you'll agree that if I have a particular value of x sub I can compute its p-value, right?
Right.
And that p-value I can call a new observed variable.
Yeah.
So I can plot my alpha sub I versus I over n. And the significance of I over n is that the probability of x less than or equal to x sub I and I'll write this empirically, in our data is just I over n. So this and this are computing the same thing. They should agree with each other if H0 actually emitted the data. So okay, so this is a basic plot that we can do whenever we want to evaluate multiple p-values. One thing that's sort of interesting to point out is that when you focus now on the low p-value tail of this, you'll note that it agrees with the Bioinformatics correction, right? Because the smallest empirical p-value we're going to get, right, is going to be, by definition, 1 over n, right? That's I over n for my smallest I, which is just 1, right? So unless I see a substantial deviation from that diagonal, right? In other words, the p-value much less than I over n, I wouldn't call it as being significant. It's not off diagonal, right? And that's more or less just in straight agreement with the whole idea of the Bioinformatics correction, that you have to basically, set your alpha sort of equal to 1 over n if you want to get one or fewer false positives on in multiple p-value tests, right? Does that make sense? So here what we're seeing is the Bioinformatics correction and this whole idea of plotting the empirical CDF versus the calculated p-value. They basically agree with each other, in this criterion of looking for off-diagonal p-values at the low p-value tail of this plot. Any questions about that point? Okay, well, if you have questions on homework 4 or whatever, I'm having office hours now, so come to office hours.